Okay, recording. Hello and welcome to the Ethereum Engineering Group meetup. My name is Peter Robinson, and today I'm happy to welcome Olivia and Alex to the meetup, and they're going to present on a new algorithm and protocol. So Olivia and Alexandre, do you want to maybe introduce yourselves and give a very brief introduction to what you're going to talk about today?
Okay, Alexandre and I are with Begassat in the Paris office. Our team, mainly Alex's side of the team, has been working on implementing rollups in various forms, anonymous, semi-anonymous, and other forms of rollups. And there's been a huge focus on practicality, getting numbers down to a practical level and to make rollups realizable in real life. And this work that we're going to present, the main idea, which is due to Alexandre, is an attempt to get hashing, which is one of the main pain points in rollups, getting hashing costs down when, for Snarks basically. So all the stuff that happens when you try to prove a correct state transition in a rollup, in a Snark proof for a rollup, all of this is extremely expensive and limits the throughput of a rollup. And so I guess you could summarize this work as being an attempt to solve this bottleneck. Maybe Alexandre can add a bit of.
That was very complete. Thanks, Olivier.
And do you want to quickly introduce yourself, Alexandre?
Yep. My name is Alex. I'm, as Olivier said, I'm working with the ETH2 Applied Research Group of Begassat. I've been working in consensus for 2 years, and as Olivier said, what we're going to present is an idea that that attempt to help proving knowledge of hashes in a very efficient manner, which is helpful as we often, especially in rollup, need to do plenty of hashes, for instance, Merkle proof verification, signatures, stuff like this. And so that's what we are going to present.
All right, sounds awesome. So Olivia, do you want to share your screen and share your slides?
Okay, can you all see my slides down to the bottom? I've had a lot of problems with that part actually in the past. Can you all see?
Yeah, it looks good.
Yeah. Okay. Thank you. Okay. Thank you for coming. This presentation will be, so as we already mentioned, this will be about a way of making hashes far more efficient within a SNARK. So making hash verifications a lot more efficient than they currently are in a SNARK proof. And so this builds on mainly the GKR protocol, which is a protocol that is fairly recent, which is a proof system. And so a lot of the talk will be focused on giving you an insight into GKR itself. GKR so this proof system GKR builds on another protocol, which is called Sumcheck. And so the first third of the talk, I guess, will be devoted to, or the first third to a half of the talk would be devoted to Sumcheck and GKR. And at the end, we will also discuss how we integrate all this stuff in a SNARK circuit. But to, just so as to not bury the lead, the central idea of this, if we boil things down to their absolute bare minimum, the central idea, which I already mentioned is due to Alexandre, is that we can, and maybe we probably should, in SNARK proofs, get rid of actual hash computations as one would implement them naively in a SNARK circuit, and replace these computations with a circuit that verifies a GKR proof, and use the SNARK circuit to carry out this verification. So that's the bare bones version, or how to say, this is the central idea. And the remarkable thing is that this produces incredible gains in performance, because this GKR protocol is very efficient, especially as it, well, as is customary with SNARKs in general, but well, it's very efficient in testing stuff, which is, for instance, algebraic hash functions, variants on MIMC. But okay, just to say again, it's basically sticking GKR in a SNARK. So we have a blog post which Alexandre and I wrote together or collaborated on, which is for which a link is provided in the slides. And so this contains a little bit more detail. And so this talk, I guess, could be seen as a way of easing you into this, this paper if you feel so inclined. Okay, so let's start at the beginning and tell you about this Sumcheck protocol. The Sumcheck protocol is a very nice protocol, which dates, I think, back to the late 80s or early 90s, if I remember correctly, which allows a prover to convince a verifier of a certain computation, which in this case is summing a huge number of terms. And it allows, through a multi-round interactive protocol, the prover to convince the verifier that this enormous sum equals a certain value. And it does so in polynomial time, whereas the sum itself would be of exponential size. It can be made non-interactive by means of this Fiat-Shamir heuristic. And to give a little bit more detail, concretely, what does it mean? It means that a prover makes a claim of the form, well, we have a function which we're both interested in, f, which is defined on some hypercube, so 0, 1 to the power n. So you can think, for instance, it's a Boolean function. And the prover claims that if you sum over all values of that function on this hypercube, then the output, the value of the sum, is a given number n. And Sumcheck is a means by which a prover can convince the verifier in very few steps or very few interactions that this claim is correct. And to put it in slightly more detail, very few steps means polynomial in n, where n is the logarithm of the domain, basically. And exponential is, of course, the size of the domain, which in this case would be very large, 2 to the n. Okay, so this seems like maybe a bit of a contrived problem initially, and one wonders why, well, one may wonder why this is interesting. I can give you a concrete example of how this is relevant using one of the classical problems of computer science, which is this satisfiability problem of a Boolean function or a Boolean formula. So if you have a Boolean formula, for instance, well, any instance, let's say, of 3 sets of this particular form for Boolean functions, three conjunctive normal form. A classical question asks, and a classical question, which is one of the first problems that was historically recognized as being NP complete. A classical question is there an assignment that returns 1? Is this Boolean formula satisfiable? And in this case, it is of note that it is relatively simple to convince a verifier of a positive answer to this question. It's enough to just provide them a satisfying assignment. And a related question, which is seemingly much harder, is that which asks not whether this formula is satisfiable, but how many times it is satisfiable. How many assignments of the variables x1 through xn, how many assignments produce 1 as an output, or true as an output if you want. So this problem is called counting 3-sat, and it's not as obvious what kind of complexity this would fall into. On the face of it, if you are a powerful prover, you may just well, do the work and actually compute the number of satisfying assignments, which basically means that you're going to run through all possible assignments of the Boolean inputs x1 through xn. And so this is basically computing a very large sum, an exponential number of terms in the sum. And since every time you compute this, the value of this Boolean function is either 0 or 1, when you sum all these values, what you get is the number of satisfying assignments of phi. So that's simple enough in theory, but it raises the question of how would you convince then the verifier of this answer? Even if you're honest and you've done this computation, how would you communicate the result to a verifier? How would the verifier tell that you're not just making up the answer? And so Sumcheck is a protocol that, among many other things, or many other similar problems, allows a prover to convince a verifier through basically, well, polynomially many steps in n, that the claimed result is actually correct. And thus, you save the verifier this task of computing this exponential number of terms. Okay, so that's basically it. On a concrete instance, this is the kind of problem that Sumcheck can solve. And everything we'll be doing builds on top of Sumcheck. GKR builds on top of Sumcheck. GKR solves a different problem, seemingly, but builds on top of Sumcheck, and then the protocol that we are proposing builds on top of GKR using SNARKs, etc. Okay, so so one of the important steps in so the Sumcheck protocol is that one should pass from, for instance, here Boolean functions, or more generally functions on some kind of a small domain. One should pass from these Boolean functions, for instance, to polynomials. And in case of a Boolean formula in three conjunctive normal form, for instance, this is rather easy because you can very easily interpolate all the terms that appear in this conjunction. So, for instance, disjunction, or the inclusive OR of 3 Boolean variables, you can interpolate by this formula, which is next to the first bullet point, and which uses a field operation. So you're really changing the domain. Instead of thinking of just truth and false, or maybe 0, 1 as inputs, you now be switching over to inputs that are field elements. And this formula interpolates this inclusive OR. And similarly, in order to represent negation, you just use 1 minus x as a function that, at least on 0, 1, interpolates the negation of x. And conjunction, so this and at least on values that are 0, 1, is interpolated by multiplication, field multiplication. And thus, still staying on this example of 3 conjunctive normal formulas, or 3-SAT, we can write this Boolean formula as a product of low degree polynomials, one for every clause in this conjunction. And as you can see, just through inspection of the first formula and the formulas and intermediate formulas, all of these polynomials ally that are just instances of this first formula, maybe with some of the x and y's and z's and swapped for 1 minus x or 1 minus y or 1 minus z. In any case, in each of these individual polynomials, the degree with respect to x, y, and z is 1. So it's this will be a crucial point. It's the formula you get will be uniformly low degree. And now this seems like, okay, it's not really interesting at this point, but we'll see how it becomes interesting. We will replace the original problem of computing the sum of this Boolean formula over all its inputs by that of summing all the values of this polynomial that interpolates the Boolean formula, in this case, I mean Boolean formula, over the same inputs. And this hasn't changed anything at this point. And here I'm just reiterating stuff I already said. So mainly the point being that this polynomial with which we replace the Boolean formula, in this case, will be uniformly low degree. But right now, it's probably not clear why that is important. So what should you remember from all of this? So what we just did was basically replace, for instance, a Boolean formula, but more generally any kind of a function on a small domain, with a new function, which in this case which will be a polynomial function, which rather than just being defined on z1 to the n, will be defined on f to the n, where f is some field that has to be large enough. And this is one of the crucial steps in in the Sumcheck protocol. It is, and it's something we'll be doing again when we talk about this GKR stuff. Extending the domain of the function you're summing over is a crucial point, because and extending it polynomially is a crucial point, because it will be, it basically will allow us to test the claim outside of the original domain, as it were. And and we'll be carrying out this interpolation step when doing the GKR stuff a few times actually. In GKR, there will be a circuit that will encode a computation. And so one of the things we'll be interpolating is a set of functions that capture the geometry of the circuit, where wires go, etc., because it's going to be a layered circuit with wires flowing out from some layer into gates at the next layer. And polynomials will also be capturing functionality of the circuit. So which of the gates are addition or multiplication gates. And polynomials will also be capturing the values that flow through the circuit. So this step of going from just set functions with domain, some kind of a hypercube or something like this, to functions that are polynomials on a small field, or on a field, I mean, that is a crucial step, and we'll be doing this many times. And just, I mean, this is not really rocket science, but this kind of interpolation stuff can always be done. If you have any kind of function f, so initially we had a Boolean function in this example, but any kind of function from z1 to the n to the field f, you can always extend in a minimal way as a multilinear polynomial, for instance, by which we mean that it's going to be of degree 1 with respect to every variable, or degree at most 1 with respect to every variable. And I'm skipping over the proof. It's just a very simple proof by recursion. You basically interpolate the function you're interested in on two opposing sides of this hypercube. You do it inductively. You interpolate the function on two opposing sides of this hypercube, 0, 1 to the n. And then you just interpolate these two functions by the formula I give below. So it's always possible, and it's trivially, it's very simple to see why it is possible. And just a slight word of caution, this procedure is not what we actually did when we a few slides back, when we introduced this polynomial that would interpolate the Boolean formula. What we did was actually, we had in this case a much nicer low degree extension of this formula, of this Boolean formula, which had this, well, why not being low degree, or as low a degree as it could be in each variable? It could be degree at most 1 in each variable. It's not that low degree, but it has the immense advantage over this low degree interpolation that you can actually compute it efficiently, and you don't need to do this memory intensive or computationally intensive interpolation step. And in Sumcheck, all that really matters is that the prover and the verifier, they have some function f that interests them, and what they need to do, that's fundamental, is that they need to agree on some low degree extension of that function. It doesn't matter whether it is the absolutely lowest degree extension of that function that you would get by this multilinear interpolation, or whether it is something that maybe is more practical for some sort of, well, for any kind of reason, but differs from the naive interpolation. What matters is that they agree on some way of extending that function to Fn, some low degree extension of that function. Okay, so I hope I basically explain what the problem is. You have some function you want to sum over all values, and you want to prove that the result is some given values, some given value. Now I'll tell you how the protocol actually works. So yeah, so as I said, Sumcheck allows you to solve, allows a prover to convince a verifier in polynomial time of an equality of the following kind: a big sum, exponential size sum of some low degree polynomial equals a given value. And now from now on, it's important that this polynomial function is uniformly low degree in each variable. So for instance, of degree at most 1 in every variable, or of degree at most something in every variable. And for this to be possible, the verifier will either be required to be able to compute P itself on some specific input, or be able to request get Oracle access to values of this polynomial function. And the real very nice thing is that yeah, this, yeah, I think yeah, this opposition between this polynomial time verification for an exponential size computation, and that's, yeah, I guess that's where GKR in particular gets its efficiency from. And what is the idea? Well, the idea is to convert this single statement, which involves this gigantic sum, into a sequence of many auxiliary statements that will be far easier to check. And there's going to be n of these statements. Each of these auxiliary statements is of exactly the same kind as the one just produced, or the one just above, except that every time you kill one of the variables. So after n rounds of this, you will have killed all the variables. And the final step is a confrontation between some predicted value of a very low degree polynomial that the prover will have provided to you, and a confrontation between this predicted value by the prover and an oracle supplied value that the verifier will request. And it's this confrontation that is going to be basically the pivotal step in the argument. All the intermediate steps, if the prover is dishonest, he can lie extremely easily at all the intermediate steps. But the confrontation that happens at the very end is the part of this Sumcheck protocol where, well, either you are incredibly lucky in a sense that, well, you that defies all expectations and you produce this incredibly rare random collision, or you're unlucky as an, or you're actually in the general case not going to produce this collision as a dishonest prover, and the protocol will return that, well, the claim is either false or you've been lying. And so this chain of auxiliary statements will connect the original statement to this confrontation from this random, from a random evaluation of P to an evaluation of a low degree polynomial. Okay, so let's dive into the weeds, how this goes. So you have this polynomial that you and the prover and the verifier have agreed upon. It interpolates a function both people are interested in and is, as I said, uniformly low degree with respect to all variables. And so the prover and verifier will exchange information in a way that I'm not going to be completely formal about, but I will explain as a conversation between the two. So, and it's going to be a sequence of auxiliary statements. So initially the prover says, okay, I claim that a certain, the sum of this polynomial we've agreed upon over this domain is this initial value n, which we here relabel as being v0, as the 0th value. And the verifier asks for proof, and so the first step of this protocol sees the prover compute this auxiliary univariate polynomial, so single variable polynomial. This involves a large sum that the prover has to carry out on their side. They have to, well, to sum over a domain which is now contains one less variable to sum over. And by assumption, the polynomial you get by doing this big sum, by assumption about uniformly low degreeness, this will produce a polynomial that is of degree at most d. And in order for the prover to communicate the result to the verifier, the prover just has to give the verifier these d coefficients of this polynomial. And at this point, the verifier is unable to check the validity of this proof or of this claim. But a very simple thing the verifier can do is to see, okay, well, if I plug in 0 and 1, respectively, into this variable x1, then plugging in 0, I will have summed over all n tuples that start with the first coordinate being 0. Plugging in 1, I will have summed the sum all the values of the original polynomials over all n tuples that start with 1. Well, if I add these two things together, I should obtain again the claimed value v0 or n. And this is very simple to do for the verifier because you're just evaluating a degree d polynomial that you would just get, but it can be done in d steps basically. And this is an incredibly simple check, but of course, a malicious prover can fool the verifier at this step. It all comes together at the end, as I said earlier. But it's a check you have to do nonetheless. And so this test, you easily pass it, and then you move on to the next round. And the next round is basically the same idea again. The verifier, well, slightly different. The verifier now chooses a random element R1 and computes the previous polynomial, the single variable polynomial at this value R1. And they want basically proof of the fact that The next step is basically of a similar nature as earlier. You have now a very large sum that involves these variables B2 through Bn, but B2 having been, or B, you want to, let me say this again, you have a similar statement, a very large sum equals to V1 now. And this very large sum is over domain, which is Z1 to the n-1, and you're going to do exactly the same step again. You want a proof of this fact, and so the prover will compute this sum, which now involves this random input by the verifier, and this sum again has one variable missing. The B2 variable is missing from this sum, and the prover computes this and provides the verifier with this again univariate low degree polynomial. And the verifier, again, not wanting to carry out exactly this computation, because the whole point of this is for the verifier not to have to do these big sums. The verifier cannot verify the validity of this claim, but again, the verifier can do this simple check that is a coherence check or consistency check, I should say. And this costs nothing and is really not secure at this point, but they can just do this verification and see that at least on the face of it, it's not completely absurd that this polynomial that they were just given P2 is as claimed. And this carries on. Again, the verifier chooses a random R2, sends it to the prover computes this giant sum, which now has two coordinates fixed, R1 and R2. And you're going to sum over all the variables B4 through Bn, and X3 is going to be this formal variable. And again, this is an exponential sized sum, and the verifier is unable to check it or doesn't want to check it. But they can do, again, these very simple consistency checks from round to round. And this carries on. You basically insert more and more of these random RIs, and you do these consistency checks at every round. And at the very last round, the verifier gives this final challenge, this Rn-1, this random evaluation point, and gives it to the prover. The prover does this final computation, which actually at this point the verifier could do themselves if they wanted to, having Oracle access to the values of P. And again, the same stuff happens. The prover computes this sum, which now is rather small actually, and provides the result, which is again a low degree univariate polynomial to the verifier. And the verifier does this very last consistency check or coherence check. And again, this is very easy to fool, to be dishonest about, but the final round basically brings this all together. You have this univariate polynomial, which is the initial polynomial evaluated where all the variables except the last one have been fixed. And as a verifier, you're now going to do the same thing, except you're not going to interact with the prover anymore. You draw a random Rn, and you're going to plug it into this final polynomial that you were provided with, Pn. And at this point, the confrontation happens. On one side, you have Pn, which was provided to you by the verifier, by the prover, which is a low degree, that is degree at most D polynomial, which you can evaluate very efficiently at this random point. This is the left-hand side, and the right-hand side is this value that you are either able to compute on your own, in case, for instance, of 3-sat, because it has this very compact representation, or it is a value that you request Oracle access to, or by an Oracle. And this is basically where everything comes together. This is the point where this producing a random collision between this low degree function on this immense domain, which is this field, and this oracle value, this is where, well, something, either you have an incredible stroke of luck of the order of like, I don't know, a chance in basically 2 to the 256 or something, or what is more reasonable, whenever you've been lying, you're not going to be producing this collision, this random collision. Okay, and so this is basically this idea of a Sumcheck. The original statement is transformed into a sequence of related but simpler auxiliary statements that lead from the original statement to a confrontation between some low-degree polynomial that was provided to you by the prover and a value that is predicted by an oracle. And if you want, just to make this slightly more precise, if you want to evaluate the odds of proving or of fooling the test, well, at some point in this chain of auxiliary statements, you would have to be able to produce a collision between this false polynomial that was provided by the prover and the real polynomial that would have been provided by an honest prover. And so since both of these are of degree at most d, and you have n rounds, basically the proof, the probability of producing this collision is basically n, which is the number of rounds and the number of variables over which you're summing, times d, which is this uniform bound on the degree, divided by the size of the field. So if you think in concrete terms, f might be 256-bit prime field, d in the case of GKR will be 3 or something very small of that size, and n will be basically logarithmic in the number of hashing, the number of hashes you'll be doing. So it will be something, some 2 or 3 digit number at most. So basically the chances of fooling the test are roughly something like 1 in 2 to the 250 or 240 or something. So it doesn't happen. Okay, so this is basically this Sumcheck, and let me just see how I'm doing in terms of time.
You're just fine.
Okay, so I guess I'll be handing it over to Alexandre almost now. Sumcheck, as I said, is the central ingredient to GKR, and GKR is the stuff that will be sticking into SNARKs later. So let me just hand it off to Alexandre. But maybe before I do this, maybe I can. Maybe there's something I could clarify for people in case they want it at this point.
So are there any questions?
Okay, it seems not. Okay, so Alexandre, I'll stop sharing my screen, and you can share yours, I guess. Oops.
Yep, I guess we can do it. Also, my software for the slide presentation won't be as good as Olivier's, so it will be scrolling. Okay, can you see it? I have a green marker in the middle of my screen. I don't know if you have the full screen.
Full screen,
we have
but
the full
also the
screen.
marker.
Okay, okay. Okay, it's only on my side then. Fine. Okay, so the GKR protocol it allows to build is a proof system. which lets you prove knowledge of satisfiability of layered arithmetic circuits. So if you're familiar with zero knowledge, you may, with zero knowledge proof system, or SNARKs, or for instance, Gross 16, you know that proving the execution of a program can be represented as proving satisfiability of an arithmetic circuit. In most of the case, what you have encountered would be what is called an R1CS, which is, so this is not an R1CS, this is a layered arithmetic circuit. The main difference is that in layered arithmetic circuit, you indeed have propagation of values. For instance, we have an input layers in the circuit, and we have an output layer. So the computation happen layers after layers, and each layer takes input from the previous one and feeds the next one. While in an R1CS, you can do a circle of dependencies, you can do everything you want. So it's less powerful than R1CS. But even which makes it, for instance, difficult to use it to compute binary decomposition in this circuit. So if you have a number and would like to do something with the bits that compose this number, then it would be difficult to do it in a layered arithmetic circuit. You would have to feed the binary decomposition as an input and just make sure that you get the whole number at the end, so that the binary decomposition is correct. But you cannot do something more efficient than this. While in R1CS, you could just pass your number and notice. So we don't have efficient bit decomposition in a layered arithmetic circuit. We have we can totally use it for something that is completely algebraic, does not require division, and can be computed in a feed-forward way. So what we use as an instance of the, as an instance, you could take a GMIMC, which is a hash function, and this is mostly why we thought this protocol was interesting, because we could apply it for hash function. So yep, another particularity is that we work with data parallel circuit. So what this means is that the circuit is going to consist in several instances of the same circuit repeated many times. For instance, one of the subcircuits would be a circuit computing a hash, and we would have in one single circuit plenty of hash subcircuits responsible for checking computation of a hash. And it happens that we can make GKR protocol more efficient in this context, which is especially nice for us. So how does it work? So I'm going to use the slides instead of just the diagram. So yep. The question is, as I said, as we work with layered arithmetic circuit, we take each layer take input only from the previous one, and so what we have to prove is that if the layer I and layer I plus 1 are consistent, each layer I plus 2 is consistent with I plus 1, etc. And this is how we are going to proceed. So in order to do it, okay. this is just explained already. So what we are going to do is we are going to represent for each the computation for each layer as a multilinear polynomial. And basically what we are going to do is to claim the evaluation of one of those circuits, of one of those polynomial, and reduce it as a Sumcheck on the previous one. So the way it works. Okay, circuit geometry explain. No. Okay. So the way it works is that we are going to define the wiring between each layer first. And this wiring is going to tell us how to do this Sumcheck reduction from one layer to the previous one. The circuit depth is the number of layers, and the breadth is basically the number of gates for each layers. So it can be also seen as number of gates per subcircuit times the number of circuits, of course. And we have what we call the wire predicate. That is a function. There is one wire predicate for each layer, and the wire predicate is going to tell you if each gate is an addition gate or a multiplication gate, and also it is going to tell us which are the inputs of this gate, or rather are those particular gates inputs of this gate. So this one represents the gate in the layer I that we are interested in, and those gates are representing and those Boolean vectors are representing, sorry, the gates from the previous layer we are taking it. And the idea is that we return 1 if this particular gate is an addition or a multiplication gate, depending on which function we talk about, from this one as a left input and this one as a right input. Okay. Okay, so yeah, as I said, this idea is that those two functions capture the geometry of the circuit. Okay, so now we need to introduce the function val. So val is representing the values in each layers of the circuits. Yeah, it can seem confusing, but I'm going to come back in the diagram slide just to explain again what is doing add and mul and what are doing val. So val is represents the value taken by each gate. So there is as many val functions as there are layers. Where I is indexing the layer we are talking about. So basically, val D contains the input of the computation, and val 1 contains its outputs. And val I more generally contains the intermediate values of the computation. And yeah, as I said, the big idea of the GKR protocol is to say if I have vol D, that I should have this vol D -1, etc. By doing consistency checks. Yeah, and also, yeah, we require that vol D, the input and the output of the computation, are known to the verifier. So to sum up, we have we have a layered arithmetic circuit representing many hash computation. We have a vector of inputs which is going to represent the element we want to hash, and as an output, so val1 will represent the hash values, and we just want to prove that val1 and val-d are consistent with respect to the hashing circuit. Okay. So yeah, the consistency check between two layers amount to this one. So the basic idea is that we are going to during the execution of the protocol, the prover will have to prove that he knows that the value val I of some random challenge is equal to something. And in order to do this, he's going to say, hey, if I'm right saying that val I equal this value that I claim, then we can transform this claim into a claim on the previous layer, because we are going from the output to the input in the consistencies. So if val I is correct, then this expression involving val I plus 1 is correct. And as we can see, it is a sum, and this is where the sum check is going to be helpful to us. Because as we viewed with Olivier, the sum check includes many intermediate steps, and at the end we have to evaluate this polynomial. Now this is very trivial to evaluate. Add I and multi I are very fast to evaluate for the verifier, so it almost doesn't count. However, the value of val I, all, and R can be more computation heavy, but once we need to go to, we need the verifier to perform one of those evaluation, we can only say, hey, here's the results. You could do another sum check and recurse again on the previous layer, and so on until we go at the until we reach the first layer. Okay, so yeah, yes. So at the beginning, add I and multi I are defined as Boolean function, but in practice, in order to perform the sum check, as I said, we're going to use the interpolation, their arithmetization, so their interpolation by multilinear polynomial. Okay. Okay. Yeah. Okay. So this explained that, yeah, the idea is that I have a claim of Fi, so I'm going to do a sum check over this expression, and at the end, no, not on Fi. Fi is a claim I get at the end when I do the litmus test. So as a verifier, I'm going to compute this and this. And the prover is going to send me the value of val I plus 1L and val plus 1R. And I'm going to be able to check that the value that the verifier give me are consistent with the value of Fi that it claimed earlier. And now I had one evaluation of val I on a random point. Now I have two evaluations. But this is not too big of a problem, because we can mix this evaluation to only get to do a single one, which is what is called in the GKR literature the mini protocol. Yeah. So in fact, what we do is that it's going to evaluate a random linear combination of those, and this is going to and in fact, when we do which can be represented as a linear combination of an expression like this, and we can factor away, but they have the same by L and R. So we can factor it to put it there, and we get this expression for the next consistency check. This is still very quick to evaluate here. And so we can move so on until we reach the first layer. And at the end, the only thing that is left to us is a complete evaluation of val1. Which can be done with only one constraint per element in the vector. So it's very, at the end, it's very quick. Okay. So to sum up what we have to do. Yep. Okay. So that's this one is explained with more details how we can go from two Sumcheck evaluation to only a single one by merging them in the add and mul factors inside the expression. Actually factoring more than merging, but you get it. Okay. Okay, so as I said at the end, we don't use the technique of recursing through a Sumcheck to the previous layer because there is no previous layer. We actually do the interpolation and the litmus test as specified in the basic Sumcheck protocol. Yeah. So yeah. A few observations. Most of the time, the prover spends on is doing some checks. For some checks, there is almost no cryptography involved. We just have to generate random challenge, but those random challenge can be generated using hash function. And if we do if we go through the total of hash function that the hash we have to do in order to perform the protocol compared to the number of hash that we prove computation of, we can see that the first one is grows logarithmically compared to the second one, which is nice. For the rest, the verifier is linear, but linear only in the number of input and output of the circuit. So if I want to check plenty of hash for two elements into one, it means that I'm going to have 3 multiplication per each time I want to prove the hash of 2 elements equal to a third one. And also, I'm not doing fancy elliptic curve cryptography. I'm just using hashes. So this is pretty neat because that means that I can easily recurse it into another proof system. And I'm guaranteed that it will be compatible for any, almost guaranteed that it's going to be compatible for any elliptic curve setup. So that's one of the reasons why we thought that this protocol was interesting. And that's also why we thought that it would be interesting, especially for rollups, as we could use it for proving hashes. So in order to do it, we designed a specific layered arithmetic circuit that would be especially efficient computing GMIMC hash function. That is the first point. And also we optimized a bit in order to make the evaluation of a GKR protocol more efficient in a Groth 16 circuit. So yeah. So yeah, that's, I don't know if you are familiar with recursive snark. Maybe I could just, it's fairly, it can be easily explained. So yeah, usually what we do is I have done a computation and I prove to a verifier that I did it, and I can convince this verifier that I satisfied an arithmetic circuit. But what you could do is also make a zero knowledge, create a zero knowledge proof. Take this zero knowledge proof and make another zero knowledge proof that you verified the first zero knowledge proof, and pass it to the verifier. And this is what we call recursion. Usually when we do this kind of thing, it requires a very specific set of curve, and there are a lot of constraints of using recursion. But in this case, it would be a recursion GKR into Groth 16, and GKR does not need any specific, anything specific for elliptic curve. So we could just push it, it's gonna work, which is nice. And so the big idea is that in a rollup, we have big circuits that compute and check computation of many hashes. So we could just offload the computation of those hashes to the GKR circuit and then verify the GKR proof inside the rollup circuits. And by doing this, it would mostly almost annihilate the constraint cost of the hashes. And also, we don't have any public value. We don't have any toxic waste setup, or it's quantum. I think it's safe to say it's quantum safe, as it relies solely on the Sumcheck and information theoric cryptography. And also it has an incredibly fast prover, where incredibly means up to from 50 up to 200 times faster than just naively computing the hashes, which is in fact the main benefit of GKR. The reason why it is not so expensive for the prover is because the prover is not asked to perform that many cryptographic operations. And in fact, he is not going to perform more cryptographic operations than the verifier. What he is going to do is only a ton of addition, which can be arranged in some way to do it in to make it linear in the circuit complexity. And at the end, we get something like the cost of computing the proof is only 20 times the cost of doing the prover Sumcheck is only 20 times the cost of just adding everything. So that's really interesting. The technique to do it is from the Libras paper. So if you're interested, you can have a look to it. It's very well explained. Okay, so yeah, I explained already the verification cost and the proof production cost. Yeah. Okay. So as I said, usually when we decompose the circuit into the same subcircuit repeated many times, we can make the prover even faster. So this is also how we make the prover fast. And this part is explained in, I don't remember the name of the article. We got have a look at the HackMD document. Okay. So yeah, there is a cryptographic part for the verifier. Basically, there is a cryptographic part that is going to be logarithmic size and have a logarithmic runtime compared to the size of the statement. But the big bit is going to be the final litmus test, which is an interpolation. There is a last part that we didn't talk about, which is how do I, what would be the initial randomness? So as I said, the first thing we do in the GKR protocol is we have the output vector. We ask the verifier to send a challenge and a challenge point, and the prover interprets this vector as a multilinear polynomial, and will evaluate this polynomial at the random point, and this is what we call the initial randomness. Usually, when we perform Fayette-Shamir for those things, it would require the prover to hash the output vector and use the result as a seed to generate the initial randomness. The problem is that we especially want to are trying to avoid this because that means that we would have to perform many hashes, and the point of in the gross 16 circuit, and the point of GKR is to not perform many hashes when you are a verifier. So we proposed two at research posts. One of them happened to be flawed, but the second one is based on Peterson commitment, or Peterson vector commitment, or sometimes called Peterson hash, and it still stands. So basically, the idea is to hack through the gross 16, and yeah, so we are going to so in the gross 16 proof, so the outer proof, the prover is going to simply say hey, okay, this is a commitment to the values, and we are going to use the value of the commitment in order to generate the randomness. And so that means that we use the gross 16 prover in order to perform the initial randomness of the inner GKR prover. So voila. I have been a bit quicker than I expected to. So if you have any question, we still have plenty of time. 20 minutes, I think. Yep.
So I don't have a question really. This has been awesome, and I can't say I've understood everything, but I've certainly learnt an awful lot. So thank you very much. Yeah. So are there any other questions though?
I just wanted to ask, clarify, to check that I understood correctly. So basically, what you are doing is, rather than coding the hash function in a circuit, and then when you need to compute the proof, basically you need to feed the witness and then calculate the values at each of the gates and then compute the ZK proof. Rather than doing that, you code the GKR protocol in the circuit, and that helps because normally in a hash function you have a different field compared to the field that you use to code the gates, whereas with GKR you have the same field, and this basically helps in speeding up the proof because you don't have this, you don't have to change the field. Is that the main reason why it's quicker?
Yes, exactly. Exactly.
Well, there's also the fact that when you if you wanted to check hashes in a SNARK circuit, you would actually encode the actual hash computation as a part of the circuit. And here the circuit does not do this computation. It verifies another proof system, this GKR proof system. It verifies a proof of hashing expressed in that proof system. So it is almost like a kind of a recursive proof, except that it doesn't have the drawbacks that recursive proofs usually used in SNARKs have, which is you don't need another good elliptic curve on top of the SNARK elliptic curve. You don't have to, there's all this business that falls to the wayside with respect to having a good tower or cycle of curves, which doesn't appear here because the verification, the GKR verification bit, is carried out purely in terms of the field arithmetic which is natural for the SNARK. And so it is almost like a kind of recursive proof, but not double SNARK, but SNARK verifying a GKR. And GKR verification is incredibly efficient.
Okay, thanks.
If there aren't any more questions, maybe flip to the last slide and I'll quickly talk about the future talks.
Okay.
Yeah, thank you. So in 2 weeks' time, I'm going to be talking about applications of blockchain. And for those of you living in Europe, you'll have to get up early for that one because that's would start 4.5 hours earlier than this meetup talk. And then in a month's time, we've got a talk on MetaMask, which will be 9 a.m. Brisbane, so evening in Europe. That talk may end up getting pushed out by 2 weeks, and we may have another talk slip in to that slot, though that's still up in the air. So look, thank you very much, Olivia and Alex again. That was a great talk. If anyone has any further questions, I suggest that we're going to post the YouTube video of this and maybe put comments into the YouTube video, and I'm sure Olivia and Alex will respond. So maybe we'll do a YouTube clap, or rather, yeah, Zoom clap. Right. Thank you.
Thank you very much.
Thank you very much.
Thank you.
All right. Yeah. Bye-bye.
Bye.
Bye. Bye.